Hello, everyone. Welcome. My name is Qing. I work for the Tech Europe sales team. And today we have Mr. Stuart Baskcomb as our speaker. And he's an engineer at Delta System Solutions. And he will be discussing how safety and reliability engineering drives sustainability in aerospace. And here comes him.
Hi, hello everybody. Good morning. So as was just mentioned, my name's Stuart Baskcomb. I'm a safety and reliability engineer at Delta System Solutions. I'm also one of the co-founders, and we specialize in safety and reliability for aerospace. And I've been involved around over 25 years now in systems and system safety and reliability. I'm going to turn my my video off, and whilst I go through the presentation, and then I'll come back on for any Q&A at the end. Okay. Okay. So how safety and reliability engineering drives sustainability base. I realized recently that I actually had a slightly wrong title here, and what it actually should say is how safety and reliability can drive sustainability in aerospace, because it relies on forward-thinking companies to exploit the analysis for the benefits of sustainability. So what I'm going to go through today is, first of all, give you a little overview of what safety and reliability is all about in aerospace and how it's used in aircraft certification. Then I'll talk about the relationship between safety and reliability and the environment, which is not something that's immediately obvious to most people. But hopefully after today, it'll be a bit clearer for you. So what is safety? The general public's definition might well be that safety means there are no accidents, etc. But in reality and in aerospace, it's recognized that faults and failures will occur, and zero accidents and zero incidents are unachievable. So the focus is on containing any failures or errors before they become an accident. There are generally two approaches to safety. Firstly, if you're conducting operations at an airport or an airline, for example, then you normally try to implement lines of defense. And the pictures you see here is taken from Reason's Swiss cheese model, which is quite a neat way to summarize it. So if you don't imagine these as kind of a static picture, these slices of cheese are moving, the holes are growing and moving as well. But you basically have a hazard at one end and an accident at the other. And on a bad day when things are going wrong for you, those holes line up and your hazard turns into an accident. So as an example, a hazard could be at an airport. There's a closed runway for maintenance, so you have to use the second runway, and the accident would be an aircraft mistakenly using the closed runway and crashing into all the construction equipment. The sort of example slices that you can have as a kind of lines of defense would be related to the equipment. So equipment on the aircraft, equipment at the airport, signage and markings, things like this. Procedures that you have in place for your organization, training, as well as oversight and independent audits. All these kind of things contribute to the lines of defence. And the holes would occur because you have an equipment fault, for example, or there's a procedure that is just inadequate, or your training is insufficient, or the culture is not very good in the organisation. And there's obviously a good, relatively recent example, a good bad example, yeah, that with the Boeing Max cases, where the holes obviously did line up, unfortunately. The second approach, generally speaking, is where you predict the scenarios that could contribute to an accident and their likelihood of occurrence. And this is what would normally take place for an aircraft development. So obviously before it's flown, there's a lot of safety reliability analysis conducted. And as an example, you would identify a hazard, say complete loss of thrust of an aircraft. That would be catastrophic, as I'm sure you can imagine, and resulting in an accident. And then EASA, who are the certification authority, would give you a requirement that you've got to predict and demonstrate with, for example, fault tree analysis here, that the probability of that loss of thrust is below 10 to the minus 9 per flight hour. So you do your analysis and hopefully show that that you're okay on that one. The way we conduct it in a development program, the way we would conduct the safety reliability analysis, it can be summarized in a V model concept. So the name comes from the shape of the blue arrows that you see there. And you look at this from left to right is time. So in the top left corner, you've got your start of the project, and at the top right corner, the aircraft is certified and allowed to fly, hopefully. And top to bottom is the detail of the work of the analysis that you're conducting from a safety and reliability point of view. So you would at the top level, you have aircraft level analysis, and then you come down through systems and subsystems, items, etc. So at the bottom of that V, where software and hardware is being designed and tested, and so the reliability and safety analysis goes right down from the complete aircraft to every single resistor, capacitor, nuts and bolts. It really looks at everything. And the left-hand side of the V is where you are essentially setting your requirements, yeah, and you're kind of validating the intended architecture of the aircraft and its systems. And then the right-hand side, going back up, is you demonstrating that you have met the requirements that you've defined and broken down on the left. Okay, so when should safety start in a aircraft development program? Essentially, it can't start too soon. So what this chart shows you on the left here is that the flexibility of the design, so your ability to make changes, is relatively easy at the beginning. Yeah, the flexibility is high, which means that the cost is low. And as you go through your projects and you make architectural decisions, you conduct lots of testing, lots of analysis, and you get towards certifying your aircraft at the end of your project, the design flexibility is very, very low, because you're fixing things. And that essentially means that if the safety analysis is not conducted till near the end, and you identify there needs to be a change in the design, then that change is going to be expensive. So the sooner you start safety, the better. So that's safety. What about reliability? So you see there on the slides a really catchy definition that I'm sure you won't remember as soon as I move on to the next slide. But what does that mean in practice? For aerospace, reliability has kind of two areas of focus. One is where you're looking at the equipment. So you're looking at, for example, a resistor. How can it fail? So it could fail short circuit, for example. What's the failure rate of that occurring? Or what's the probability of a sensor losing its output? And this sort of information is vital and underpins the safety work. But also on the operational sides, at an aircraft level and a fleet of aircraft level, reliability plays a key role. You want to be able to have your aircraft available for use when you want it. So and it needs to fly when you want it to fly. So there's a lot of reliability analysis goes into availability of the aircraft and the dispatch availability and this kind of thing. Okay. So the question is, does reliable automatically mean that you're safe? Safety certainly can be improved if you have high reliability of your equipment. Obviously, if you have less failures, you have a lower risk of an unsafe condition. But you can't. The reliability can't affect what happens afterwards. So your resistor fails short circuit, and you could do some analysis, you could do some testing, and make the failure rate of that resistor failing as low as possible. But what happens in the system and on the aircraft afterwards is not to do with reliability. And if you think back to the earlier slide with the safety definition, it's how to contain these failures. So safety looks at the failure effects as well as then the probability of those occurring. And this means that you can have an unsafe system with lots of reliable components. And on the other hand, you can also have a safe system with lots of unreliable components. So you could make a safe aircraft system where you have to change components or equipment after every flight, for example. So in practice, it doesn't work, but in theory, it does. So perhaps to put it in a more succinct way, does reliable mean safe? No, it doesn't. But as I said, they are linked inherently, and they can be used together in a smart way to help aerospace become more environmentally sustainable. And it can do this particularly with new and innovative technology that is the trend right now that you probably read about in the news anyway, for electrical aircraft, VTOLs, drones, unmanned air vehicles, as well as hybrid and electric propulsion or hydrogen propulsion as well. So how can we exploit, and when I say exploit, I mean that in the positive sense of the word, yeah, in the good sense of the word, we can exploit safety and reliability and all the very well defined and widely used methods and analysis within aerospace. We can use that to the benefits of the environment. And the first main point and the main driver of the safety and reliability analysis is to prevent accidents. And preventing accidents is has the additional benefit, especially for these new aircrafts that are under development today. It has the benefit of increasing the chances that this new industry or this new part of the industry will be accepted by the general public. If you could imagine that if there are some electric unmanned drones delivering around the city in the future, or air taxis running from an airport to a city centre. If in the early days we have some of these dropping onto the city and onto people, and there are real accidents, it won't take many for this new development to be stopped or hindered. You know, the politicians would make the decisions, and the budget holders, they will soon lose the interest and the will to legislate for this new kind of technology, and that has an impact on the environment, because this new technology is going to improve the environmental impact of aerospace. It's going to help reduce the reliance on and the use of fossil fuels. For example, if we go electric, we go hydrogen, there's improvements there. So any early accidents here are going to mean that we stick with conventional fossil fuels and kerosene for more and for longer. And that's the main one. The question is there then more that safety and reliability can do? And as a spoiler alert, yes, there is, and I'll tell you a little bit more on the next slide. Just as an aside, the pictures there on the left, I assume you know the Concorde, and you'll recognize this one. The one below it, if you remember the Swiss cheese example I mentioned earlier about the closed runway for maintenance and the airplane crashing, unfortunately that was real, and that's the result of it. Okay, so the next point in how we can exploit safety and reliability. So there's the first point was from what must be done to meet certification, preventing accidents and achieving these very low probabilities of an accident occurring. So everyone does do that. Some do it better than others. But the smart people and the smart companies can and do exploit safety and reliability analysis and engineering further by using it to optimize the design. So what safety and reliability analysis can show you is, do you need a redundant system? If you do it properly, do you need a redundant system or not? Do you need some redundant equipment? Exactly what do you need in your aircraft to be able to perform what you want it to perform in an acceptably safe and reliable level? So the analysis can be used to show that you have no unnecessary equipment, which means no unnecessary weight. And in aerospace, as I guess you can imagine, every single gram is accounted for, has to be accounted for, because it costs money, and it costs money because it means you need more fuel to carry the weight for the same distance, and not just fuel as in kerosene, but also battery, electrical power, or hydrogen. All of that is what I consider fuel in this case. And whatever that fuel is, if you need less to travel from A to B, that is clearly better for the environment. When I have these discussions with customers, we talk about it reducing costs, because that's the big focus, yeah. But I always tag on the line that it's actually better for the environment, and they do. Smart people like that as well. But it's not just optimizing the design of the equipment on the aircraft, but you can optimize the design of your operations. And again, the safety reliability analysis methods can help you with that. So what is possible is you can show when a failure occurs, when do you need to fix that failure? So you can, on modern aircraft, you can usually fly with certain failures for a certain time. So you don't have to carry out maintenance after every flight, and you can work out how long is safe to travel with those faults in place, and you can work out when you need to replace equipment. So the analysis can show you that you'll have the optimum maintenance program. You have this means you have the optimum logistic support, so you have less spares. It also can mean that you have less aircraft in your fleet, because you can work out and plan exactly when aircraft are taken in and out of service to do whatever they need to do, or there's no unexpected, unscheduled maintenance you need to do. And that also reduces costs and is better for the environment. The extra bonus for the environment by reducing costs is an extra sort of side effect, if you like, that reducing the costs means that you increase the likelihood of these businesses, these operations, like Lilium, as you see there on the right, being successful. And it means they can create a service at a better price that's more affordable, so it can be used by more of us, and it's not just for the rich and famous. And that means that more of this new technology will be flying, and all of that is also good for the environment, as I mentioned on the previous slides, that this new more environmentally friendly technology in aerospace can only be a good thing for the environment. Okay, so my final slides. You probably hear this a lot from chief engineers and directors about safety being first. So I just want to take the opportunity to say that safety is the first priority of nobody. So what I mean by this is when you hear it, it's just simply a bit of PR bull. If safety was your first priority, where would your aircraft be? I mean, if safety was my first priority, I would never let an aircraft leave the ground. I would never let any people on board or any fuel on board. So it's a load of rubbish, really. Safety has to be considered with other priorities, and it has to be balanced. Yeah, so you want the business to be successful, and you want it to be safe and reliable. So safety is one of the priorities, but it's a balancing act, and it's not the number one. Okay, then that was it from me for this session. Thank you very much for your attention. I think we have a few minutes for any questions and answers. I'll put my video back on just to show you that I'm still a real person. And thanks for your attention.
Thank you, Stuart. We do have some questions. Here come from Mr. Christoph Bowman. I'm going to show on the screen. And this is the first question he came with.
Safety consideration applied throughout engineering operation. How do you track and bring safety insights to the engineers? Yeah, good question. So the approach that we take is you need to be integrated within the system engineering teams, and work essentially alongside them. So it means that that they're your colleagues, and the communication channels are really important. So meetings, reports, and systems are all used. It's different for different companies, but the safety requirements that come out of the safety and reliability analysis normally goes into like a requirement management tool, like doors, for example, people use a lot. And then there's companies have processes, and the safety reliability analysis goes through this V diagram I showed you, where you and you produce reports at regular stages, and go through reviews and validations with the designers.
Okay, and actually he gave another comment almost right after his questions. There comes his comment. I think this is more of a comment instead of a question.
Two people share 100% responsibility. Each of them are 1% responsible. If 100 people, yeah. Yeah, I mean, there's another one where people say, safety is the responsibility of everybody, which is also another one that doesn't really work, because what's important is that you have a good culture in your organization and your development teams, and you have somebody that is focusing on safety, but everyone's involved in safety. I wouldn't say it's everyone's responsibility, but it has to be everyone involved and communicating. Yeah, if someone has a problem, if someone's got a concern, that they raise it, and if it's a minor one, even they should raise it. Particularly important for operations, because a lot of minor incidents can go unreported, and then eventually one day those minor incidents happen on the same day and it becomes an accident. So reporting and communication is really important.
Yeah, I personally agree. So, okay, here comes his last question from the same gentleman.
Yeah. Hashtag change management. Yep. So most companies, or all companies that are successful in aerospace, have a change management process as well as requirements management. So if the safety analysis shows that, or the reliability analysis shows that, this sensor or this valve or this computer is not right, we need to change something, then there's usually a change management process. So safety guy would propose the change, go through a change control board, etc.
Okay. Yes. I'm sorry to say today's time is reached. So thanks for everybody. And maybe you would like to write down the code on the screen at the moment. And this code will give you, or might give you, a chance to win a very nice souvenir from the organization. But thanks for everybody's attention, and also thanks, Stuart, for a nice speech. Okay. Have a nice day, everybody, and bye.
Thank you too. Bye, everybody.